Okay, let me start by, again, putting everything we've been doing a little bit into context. And we're getting very close to going to the Navier-Stokes equation. So I want to see whether we can see the forest through the trees for all the things we've been doing. We've been talking about vectors and tensors. And the main innovation, I guess, was that we introduced tensors. And we also learned how to do Einstein notation. So on the homework, we had a little bit of practice with this. So our Einstein notation, very simply, summary, is that when we have a vector, we just write VIEI, and that is a way of writing a vector in 3 coordinates. These coordinates, this coordinate basis, is always a Cartesian system, which is a Cartesian system, XYZ, is always constant in space. So it's constant in direction in space. Of course, it's an orthonormal coordinate system, but the other orthonormal coordinate systems we've used, the Cartesian, the cylindrical and spherical, are also orthonormal, but they're not constant in space. So this constant in space part comes up important when we deal with taking derivatives. Then also for tensors, say the tensor A, we write that in Einstein notation as A with 2 basis vectors, a sum of 9 dyad combinations. And so we need 2 subscripts, say PK, EP, EK, to get these 9 coefficients of a tensor, which could be written in a 3×3 matrix form. And then, of course, the del operator. The del operator can be del or del dot or del dot del, the 3 versions. But they all operate the same within Einstein notation. It's d by dx s e s. And then from there on, you put your vector or your tensor next to it and carry out the operations. Then the only other thing we need to know how to do is to take the dot product of either the nabla operator or a vector and a tensor or 2 tensors or 2 vectors. And what we know is that because we've dealt with these orthonormal coordinate systems, the dot of 2 unit vectors, E dot E, say EP dot ES, is the Kronecker delta, delta PS. P becomes S. And the reason P becomes S is because this product is 0 when P is not equal to S, and it's 1 when P is equal to S. So P equal to S is the only time the terms stay behind. So that's why P becomes S and all the other terms go away. And you replace the delta with a 1. P becomes S and you're done. So I'll just run through the slides that I did on this topic. The last thing we covered was the differential operator, and here's that differential operator again. The time differential operator is obvious, I think. And then here's our friend the del operator in Cartesian coordinates. And as I said before when we did this, the del operates on everything to its right. And that's why it's so important that these unit vectors be constant. So here's del of a scalar becomes a vector, the gradient of a scalar. Del of a vector becomes a tensor. Here's the tensor in sort of a disorganized grouping, but we can also write it in Einstein notation. We're going to see this a million times. And then we can do del dot of the nabla operator with an arbitrary vector, and we get a scalar, and all these combinations. Here's the Laplacian del dot del of something that appears in the Navier-Stokes. This is a vector. Don't forget these plus signs here. This is a vector where this is the x component, this is the y or the 2, this is the z or the 3. And all these different things we now know how to do. So that's what we've been working on. Then I also went through cylindrical coordinates, r theta z and r theta phi. These are pretty straightforward. These slides are a little busy, but the basic idea is to reinforce once again that when we do Einstein calculations, the unit vectors have to be constants or Cartesian, the Cartesian constants, because when we do it in, say, cylindrical coordinates, as I'm showing here, it's not easy anymore. So the whole idea of Einstein notation is easy, easy, easy. So we can do the Einstein calculations without tables, and we will on exams. We'll do calculations without tables. But when we do these calculations in spherical and cylindrical coordinates, they're not easy. It involves these coordinate transformations. And even just doing one example, as I did in class here, here's del dot v. Here's the del operator having been distributed. There it is acting on v. Here's the second term acting on v. Here's the third term acting on v. And if we just look at the second term of the del operator acting on the first term of v, it's already this complicated calculation. E theta 1 over r d by d theta of something that has to, the whole thing has to have its theta derivative taken. The whole thing has its theta derivative taken, which means we have to use the product rule. The first times the derivative of the second plus the second times the derivative of the first. That's the product rule. And then we have to go back a slide or two to these coordinate transformations to figure out how to take the derivative of e theta. So here's e theta in terms of constant basis vectors. So this, I can take the theta derivative of this, not too bad, right? Because derivative of theta of e theta is the derivative of sine, which is cosine. So it'd be minus cosine. This is a constant, so no problem. Derivative of cosine is negative sine. So that's what I did here. D by d theta of cos theta times these constants. We can then take that, and then I go back and do algebra and realize, oh, this is exactly the same as just e theta itself. And we get finally, again, oh, this algebra, we find out that this combination of the second term of the del operator operating on the first term of the v written in r theta z coordinates finally gives me this thing. So as I summarize here, it's not intuitive at all, but it shouldn't be intuitive. It's actually a very complex calculation involving geometry. So thank goodness it's been done. We don't have to redo it. We're just going to use the tables. Okay? So here's del dot v from the tables. And here's the term we derived. It's right there. We got it correct. It was because it was this second term operating on the first term, and here's the one that turned out to add in there. But then there's these other terms that turned out the way they did. So that's what we'll always be picking those off of the table. So when we do Einstein notation, we will not do Einstein notation on curvilinear coordinates. Although they're orthonormal, they are non-constant. But they are very convenient, and you saw that when you studied fluid mechanics. They do mimic the coordinate surfaces. It's very easy to define, for instance, the shape of a cylinder using cylindrical coordinates. If I have a pipe, I would much rather say, oh, this is the z direction, this is the r, and so this coordinate surface is r equals the radius. I would much rather say that than write the same thing in Cartesian coordinates, z, x, and y. And then I have to say, oh, well, x squared plus y squared is equal to r squared. And so the coordinates of this surface are this equation here, very complicated. So we will use these Cartesian coordinates, but we'll just use the nabla operator from the tables. Okay, which brings us up to date with what I've talked about so far. And now where we're heading is, okay, so what have we done? We've reviewed vectors, we've learned about tensors, we've learned this manipulation method called Einstein notation, which allows us to see how to, say, prove vector identities and manipulate in one particular type of coordinate system, the Cartesian. And that may seem very limiting. It has to be the Cartesian system. But as you'll see, we're going to be able to derive the mass and momentum balances very easily using a Cartesian system because, as I stated at the very beginning, when you have a vector or tensor system, it's independent of coordinate system. So since it's independent of coordinate system, we can pick an easy one, Cartesian, derive everything using Cartesian coordinates, and then just say, well, as long as we do the coordinate transformation correctly, we're good. We can transform it into cylindrical or spherical or bipolar or helical or any kind of crazy coordinate system that's useful to us. So when we do our derivations, we're just going to use the Cartesian coordinate system, which means we can use Einstein notation throughout our derivations. So that's where it's going to become very handy to us. So the only thing we need before we can proceed are a few more theorems from vector and tensor math, and that's what's up next. And I'm not going to prove these. You have to really take a graduate course in vector and tensor mathematics to prove them, although you can at least think about them logically. They're not too unintuitive, perhaps, once you know what the various symbols mean. So one that we're going to need to derive the Navier-Stokes and the continuity equation is the divergence theorem. So this is the divergence theorem. And it kind of works a little bit like a mass balance. So the divergence theorem is this mathematically. It says that the volume integral of this combination of properties is equal to the surface integral of this combination of properties. So what are these combinations? This is the divergence of a vector field B, and this is n dot that same vector field. So we saw in the homework that n dot v was the component of the velocity that was coming out of through a surface. And so this term is like the net flux outward of some volume enclosed by the surface S. The net outward flux is n dot b integrated over the whole surface. The left-hand side is like the volume change, the change inside the volume integrated over the volume. So this is like the rate of change inside the volume, okay, is equal to the net flux out. So for instance, if we look at an arbitrary surface, this is sort of an arbitrarily shaped surface, n is always by convention taken to be the outwardly pointing unit normal at some position in space. So here's an arbitrary position in space. Here's a little piece of surface at that location. So it has the surface has an orientation given by n. And it's saying if I add up all of the outward fluxes at every location, that will be related to this way of expressing the rate of change of that property inside the volume. In words, the integral of the divergence of a vector field over a volume is equal to the net outward flow of that property through the bounding surface. Now, this is going to be very useful to us because sometimes in our derivations it'll be handy to think of things as a volume property, sometimes as a surface property, and we'll use the divergence theorem to get from one to the other. Now, another vector formula that we'll need is Leibniz rule, which comes again from three-dimensional calculus. And it's a rule that's used for differentiating an integral. And let me write it here. We're actually going to use these right away, so we'll get a chance to understand how they're used right away. So for instance, if we have some function and we're integrating it over some defined constant limits. Okay, so this is a multivariable function, x and t. We're integrating it over some defined limits, alpha and beta. Alpha and beta are constants. Now, what happens if I want to know the rate of change with respect to the other variable? So, for instance, if x is space and t is time, what if I want to know the rate of change of this quantity that I've integrated? So, for instance, the mass integrated over some amount of space, what would be the rate of change of the mass? So, all I've done is write the rate of change next to the integral. Now the question is, how would I evaluate such a thing? And Leibniz rule tells us that because these two limits are constant, the way you do it is this comes inside as the partial derivative. We'll take that simply as a theorem. So this is a multivariable function, f of x and t. And we're saying that the rate of change of this integral is the same as the integral of this rate of change, this particular rate of change, the partial derivative with respect to time. Now the next case is an interesting one. What if these limits are not constant? Okay, so what if they're not constant? If they're not constant, then Leibniz rule is a little bit different. So now let me try a new integral. This will be the integral of f of xt. And these limits are going to be alpha as a function of time and beta as a function of time. How now do I take this derivative? And again, we can just write that derivative. But in writing this term, I haven't really done anything. Now, it may seem logical to bring this inside again, and that's only partially correct, because there's an effect of the moving limits on the ends. So this is equal to, by Leibniz rule, the partial derivative of f with respect to t, dt, plus something to do with the upper term and something to do with the lower term. So plus the rate of change of the upper term. So these are total derivatives because beta is only a function of time. The total derivative times the upper function evaluated at that limit. Okay, this is for beta, excuse me, I've had a typo here. I've been writing integral over t, and it should be over x. Okay, we're integrating over x and differentiating with respect to t. And so we evaluate the function at the upper limit. X is equal to the upper limit, so f of beta t. And then minus, just like we always do when we evaluate one upper limit, then minus the lower limit, now times the derivative of the upper limit times the lower limit, f of alpha t. So Leibniz rule tells us how to take the derivative of an integral. If these are constants, this rule still holds, in fact, because d beta dt is 0, this term goes away. D alpha dt is 0, this term goes away, and we get our original result, which is that you just take the total derivative inside to the partial. Now, on the slide here, I have the three-dimensional version, which we're not going to need, but I'll show it to you. Well, actually, we will use this one, but in its simplest form. What if we have a three-dimensional function f? Now we integrate it over a volume to get the integral j. What if we want the derivative of that with respect to one of the variables, for example, time? So this is just writing, as I've been doing, just writing the d by dt in front of the integral. And Leibniz rule says, well, you can take it inside again as the partial derivative, but you need something related to the time dependence of this, of the limits, the volume limits here. And so the correct term is a surface integral over f evaluated at the surface in this particular way. F, the velocity of the surface, dotted with the unit normal ds. We're not going to need to evaluate this term except in Chapter 9, parts of Chapter 9 that we're not going to be doing in this class. But what we can tell from this is if the volume is fixed, then this velocity of the surface is 0, and this term goes away, just like it did for the one-dimensional Leibniz rule. And we see that the total derivative of the volume integral becomes the total integral of the partial derivative. As I said, we're going to use these right away, so you're going to see what examples I might have for using why I would introduce this rule. And I have one more definition that I want to do before we actually turn to the mass balance and the momentum balance, and that's the substantial derivative. Let me start by saying that you've seen this before. If we go back to the Navier-Stokes equations, in some sense we're picking up all kinds of details that were brushed over when you first learned these topics. Rho dv dt plus v dot del v equals minus grad p plus mu del squared v plus rho g. Perhaps you've seen this left-hand side is sometimes written as dv dt, where dv dt is defined as just that stuff in parentheses, d by dt plus v dot del v. So I know that when that was introduced to me in my first course in fluid mechanics, I said, oh, okay, define anything you like. That doesn't bother me. You want to call it capital D by V dt, it doesn't affect me at all. And that works, in fact. There's no real reason that you need to know exactly why that's done. But there is actually a good reason, and we're at the stage now where we can explain it a little bit. And then I'll tell you again that in Chapter 9 in the advanced fluid mechanics, it comes up with a vengeance. Although, again, we'll be doing just a taste of Chapter 9 in this class. So I would start by asking myself, why do we do this? You know, why do people in fluid mechanics make such a big deal about this thing, which is called the substantial derivative? And let me show you, okay? The bottom line is, and this is summarized on the slides, but perhaps it'll be more clear if I just go through it. Consider this kind of three-dimensional function, f of x, y, z, and t. So this might be velocity, which it is in the Navier-Stokes equation. Now, we know from just the chain rule that we can write the differential df as the sum of the various partial derivatives, df, dx, with the other variables constant dx, plus df, dy, all other variables constant dy, plus df, dz, all other variables constant dz, plus df dt. It's a multivariable function. This would be calculus 3. And that is how we can relate through this chain rule the change, the small amount of change in the function f to changes that might take place in the various variables that make up the function f of x, y, z, and t. Now, again, going back to your Calculus 3 class when they introduced this concept, perhaps they drew some kind of a three-dimensional hill and said, okay, this is my three-dimensional function. I'm going to desperately try to do something in 3D. I'm not a very good artist. If I have some sort of a three-dimensional function, at some point, if I would go off in the x direction or go off in the y direction or go off in the z direction, there would be a slight change in my three-dimensional function f. And so back then they said, well, you can write this if I go into an arbitrary direction, by an amount df, okay, I can break that into, I can take the projection of df in the x, y, and z directions, and if I could draw in 4 dimensions, the t direction as well, and get this geometric relationship between the change in the function and the appropriate change in each of the 4 directions. So this df is true, this relationship, holds in it for any direction that I might choose. Or I could say for any path. So if I picked a path through my 4-dimensional space, although I can only sketch in 3-dimensional space, if I picked a path, an arbitrary path, at each little step I could write the df in any arbitrary direction, and I could write this function. Now here's where we get to the part that's about fluid mechanics. In fluid mechanics, we generally aren't concerned with any arbitrary direction. There are some directions we care about a lot more than others. And the direction we care about is the directions the particles go. Okay, so now let me consider something like a velocity function in space. So let's say I have some kind of a flow here, which I'll draw in 2 dimensions, maybe like this, some sort of an expansion flow. And I have particles moving along various path lines. So that means that if there's a piece of fluid here, this piece of fluid travels along this path. It's a very particular path. Now along that path, there's a velocity to this particle. So at each of these locations, it has a velocity which is changing. Okay? This velocity vector, v, is d the position vector dt. So this is dx dt, dy dt, dz dt, meaning where x is the x position of a particle. This is the y position, this is the z position. So it's a very particular path and a very particular rate of change with time. Now let's treat the velocity vector v as that arbitrary function f and write the differential dv, for instance, and form that differential the same way we did before. But we're going to choose the path. We're no longer going to say this is for an arbitrary path, which we can say straight out of Calc 3. We're going to say this is a very particular path. This is a path that the fluid particle is, in fact, following. So now I have a function f. I'll leave it as f just because I could be following the concentration as it moves along the particle path, the density of the particle as it moves along the particle path. It's going to be a function of x, y, and z and time. And df, I've written all this before, is equal to partial f with respect to x dx plus partial f with respect to y dy plus partial f with respect to z dz plus partial f with respect to t dt. If I now say choose the path to be a particle path line, then I can also divide through by dt, and I get df dt equals df dx dx dt plus partial f partial y dy dt plus partial f partial z dz dt plus partial f partial t. So all I've done there is divide through by dt. Here's where it gets kind of magical, maybe, kind of neat. These terms are very recognizable to us from the last slide. These terms are just the particle's velocity components. Because the path I've chosen is a particle path line. If I hadn't chosen a particle path line, they still wouldn't be anything. They would be the change in x with respect to the change in time, and it wouldn't have that special meaning. But because I'm sitting on a particle that's moving along and its velocity means something to do, its coordinates as I move along, the rate of change of those coordinates with time means something to me. They mean the velocity. This becomes a very special type of a derivative. So let me change this. Instead of writing it as Vx, this is going, dx dt, this will be the velocity component in the x direction. Instead of dy dt, I'll write this as the particle velocity in the y direction. And instead of dz dt, this is the particle velocity in the z direction. So now I can write my df dt equals partial f with respect to x Vx plus partial f with respect to y Vy plus partial f with respect to z Vz plus partial f with respect to t. This is, in fact, that substantial derivative. I'll move this up halfway. We can maybe recognize this as in Einstein notation. Let me change it to Einstein notation. X will be x1, y will be x2, z will be x3. This is a vector f here. This is d vector f dt equals df dx1 v1 plus df dx2 v2 plus df dx3 v3 plus df dt. Now I'll put it as a summation. This is the summation. Pick an arbitrary letter. J equals 1 to 3 of df. Actually, all the way through, I should have been having underbars on my f's. df dxj vj. And then there's one extra term, df dt. And so in Einstein notation, we drop the summation. This is df dxj vj plus df dt. And this, you can verify, is v dot del f. Vector function or scalar function, actually, the derivative, the derivation works the same. Well, let's just verify it while we're here. Over here on the side, v dot del f would be VPEP dot d by dxiei f k ek. P becomes I, vi d by dxi fk ek. df vj df dxj. These two match, it's the same thing. So going back to the prepared slides, I have the same thing written, only I did it for the scalar function here. So df, here I just write the function as the things the variables of the function. I divide through by dt, and I notice that if I choose to take the time rate of change of f along a chosen path, these dx dt, dy dt, dz dt are just velocities. So I change them into being the velocities, and that's the same as v dot del f. So df dt along a particle path, that's key, right? We can't make that change to velocities unless the path we've chosen is along a particle path. df dt along a particle path is partial f with respect to t, this spare term over here on the right, plus v dot del f. And in fact, what we'll see when we do the mass and momentum balances is that we are talking along particle paths. So when derivatives appear, we'll see directly that it's this kind of total derivative of a function that's appearing in our derivation. So that brings us to the meat of our introductory section, which is to get to Navier-Stokes equations. So what we're going to do next is derive the Navier-Stokes equations. It's going to take us a couple of lectures to do so. And then we're going to use them. In principle, you've already studied how to use them, so I hope that part is not too difficult for you. But you're going to see it now in this vector form. And one of the reasons that I'm taking the time to derive them is so that you can see what the difference is between the equations we'll use for Newtonian fluids and the equations we'll use for non-Newtonian fluids. So at some point in this derivation, we're going to have to assume Newtonian fluids. And that'll be fine for this first section, and it will match up with what you've already studied. But then, as you know, we're studying non-Newtonian fluids. So the very next topic after Newtonian fluids, we can then stop short of getting to the Navier-Stokes and say, okay, here was the point, here was the step when we assumed things were Newtonian. Here was the step when we assumed things were incompressible. And so we'll know exactly where to start again when we want to deal with, say, incompressible fluids, for example, or non-Newtonian fluids. Okay, so this, we'll probably have just enough time to do the continuity equation here. So we're starting the third chapter of the text, Newtonian fluid mechanics. We're ready to go. We have our vectors and tensors, and we have our vector theorems. We're going to derive the governing equations and learn how to solve for velocity and stress. So overall, we're going to consider a mass balance on an arbitrary volume. So that's the only thing special about deriving the continuity equation or the Navier-Stokes equation, is that we're going to choose an arbitrary volume, and it's the same one that I've looked at before, just not a very specific one. Doesn't have to be a cylinder or a sphere or a box. an arbitrary volume in space, which we say has a volume V, and it's fixed. So projecting a little bit ahead, when Leibniz rule comes up, we're not going to need that extra integral for a time-varying boundary. We're not going to let this boundary change with time. It's going to be fixed. The boundary total surface area is S. At every location on the boundary, I can identify the shape of the boundary by this little piece of surface and its unit normal n. The unit normal n will always point outwards. That matches the definitions inside our various divergence theorem, for instance. So this is a little piece ds. So the first question we ask ourselves is, what is the rate of change of mass inside this volume? And it's actually a very straightforward calculation. The rate of increase in mass is equal to the net flux in. Okay, this goes back to, in chemical engineering, the very first course in mass balances. Very simple. Rate of increase of mass in V is the net flux in. But now, because we're talking about an arbitrary volume, we need the extra math. So we're going to do what's called the microscopic mass balance. If we have an arbitrary fixed volume V, it's enclosed by a surface S. And here's the mass balance. Rate of increase of mass in V. Okay, how does it go up? It goes up because mass flows in. Net inflow of mass. Net inflow of mass into V. Now, our only challenge is to write that. And it follows the methodology of the shell balance. Okay. What is the mass? Well, I'll pick a small piece of volume dV and multiply that by the mass per volume, the density. So the mass per volume is the density rho. The little piece of volume somewhere in space is dV. That gives me mass. So this is the mass at some location in V. And now I want to sum up that mass over the entire volume V. And that's what integrals are for. Integrals are limits of sums. So this integral is the summation of all these little pieces of volume. So if I integrate this over the volume V, I've got the total mass inside the volume V. And to get the rate of change, I just take the time derivative. So this part is the total mass of my control volume. And then when I take the rate of change, this turns this into the rate of change of the total mass. So although we've never done this kind of calculation before, it's actually very understandable. All we're taking is a scalar field, the density. Okay, this is the density at any point. And I'm essentially taking my volume, and at every point I'm figuring out what mass is in that little piece of volume, and I'm just adding them up to get the total. So I have the left-hand side. Now I need the right-hand side. I need the net inflow of mass into V. And this is why I asked you to do that homework problem, so that I could do this part really quickly. The net outflow through an arbitrary small surface you showed in the homework was the density times the component of the velocity that pushes mass through a particular surface. Okay? So this, I'll redo this since we're at the very end of class. I'll redo this on Wednesday. But this is the volumetric flow rate out. So this is volume per time. This is mass per volume. So I have mass per time out, in. So the net inflow of mass, net, I didn't do net yet. The net inflow, this is the mass outflow now through the surface S. If I integrate it over the entire surface, I get the net, meaning integral, inflow, the n was the outflow coordinate, minus sign makes it inflow of mass into the surface V. So I'm out of time. Next time we'll take these two pieces and put them into the mass balance. The rate of increase of mass in V is equal to the net inflow of mass. We're going to equate these two. And you can see this is an integral over volume. This is an integral over surface. The divergence theorem is going to come to our aid and allow us to put them both as volume or both as surface. And then we can get to the continuity equation. So we'll finish that up on Wednesday.